Hi class, this class we are going to have the PCB design workshop. For this class, we are going to talk about basic knowledge of PCB, terminology of circuit design, tools to design PCB, and together we will design Arduino Uno debugger with Eagle. The board we are going to design will serve two purposes for this class. It will act as an Arduino debugger, so we can debug Arduino by pause the sketch. In another exercise, it will act as a simple logic analyzer, and we can debug Arduino by observing the signal output of an Arduino. The word PCB stands for Printed Circuit Board. It supports and connects electronic components. Why do we ever need a PCB? It is possible to create a working circuit with breadboard or proof board, but the PCB has some benefits in building circuits. For example, the PCB has much more reliable connection, and the circuit size will be much smaller. PCB is a technology ready for mass production, and for most modern PCB softwares, we can export 3D model of the board and cooperate with other 3D software, so the mechanical design will be much simpler. For example, here is the dash button circuit I designed. By exporting the circuit's 3D model and import the model into a 3D design software, I made the case that fits the circuit precisely. On the left image, the purple part is the circuit. The PCB also has some limitations. For example, most PCBs are customized order, so they cost more money than perf board, and they do take some time to fabricate. And because the fabrication and shipping takes time, it is more difficult to do a fast iteration on a PCB. PCB are often involved with surface mount part and small pitch parts, and they require advanced solder skills or soldering tools. Learning how to use a PCB design software is not as easy as a breadboard. The learning curve is much steeper. If you find an issue on your fabricated PCB, or you want to change the connection, it is difficult to reroute the circuit on a PCB. Here is an example of fixing an incorrect PCB design. The board has a wrong design and it will take 2 weeks and $2,000 to plan another batch of the board. So I have cut some traces and reroute the traces with thin wires to get the board to work. It was a messy work and it took a long time to do. For an ITP project, when should we start to consider designing PCB? PCB should be the final stage of your prototyping because it takes some time to fabricate. You can prototype with breadboard and proof board first in order to make sure the circuit works. And if you want a nice fit project or reliable circuit, and if you have enough time, at least 2 weeks, you can consider designing a PCB for your project. Here is a project I did for the digital fabrication class. On week 8, I finalized my idea. On week 9, I did the prototype to verify my idea. On week 10, I designed a circuit and placed the order for the PCB. On week 12, I designed the case. On week 13, I did the assembly work and test. It is possible to make a PCB in ITP or at home, and there are some equipment that we could use to make a PCB. Generally speaking, the in-house PCB fabrication can be done in 2 ways, milling or etching. Milling is a method to remove copper mechanically to form isolated traces from a copper clad board. There is the other mill on the floor you can use to mill a PCB, and you may refer to the subtraction class website for more info about the milling process. Etching is a method to remove copper chemically to form isolated traces from a copper clad board. The most popular in-house method is heat transfer etching. You will first laser print traces on transfer paper and use heat to transfer toner to the copper clad board. And then you can etch away all the copper that is not covered with toner. There is more info on the circuit design and prototyping class. After you get a PCB, you can do pick and place either on a machine or by hand, and you may do the reflow soldering in a reflow oven. You are encouraged to try to fabricate an in-house PCB to understand the process, but personally, I don't recommend it for your serious project or thesis, or future works after ITP. And I will explain the difference between an in-house PCB and a factory-made PCB. Here we will compare the factory-made PCB and the in-house made PCB. The in-house PCB is often made with 1-layer board. If we can align the two sides carefully, it is possible to make a 2-layer board. The factory-made PCB generally starts with 2-layer board. With more budget, the factory can make 4 layers, 6 layers, or even more layers. The copper in hole fabrication is quite difficult for in-house fabrication because it involves electrical plating. The in-house PCB often use copper eyelets to form conductor between 2 layers. However, the copper plating is a standard procedure for all PCB factories. The next difference is solder mask and silkscreen printing. They are often skipped for in-house PCB because they need extra steps and time, but they are also a standard procedure for all PCB factories. The advantage of in-house PCB is the lead time. It is possible to fabricate an in-house PCB within a few hours, but depending on the budget, the factory-made PCB will take days or weeks. The PCB design is a 2-step process. First, we design schematic. Next, we design the layout. We can go back and forth between the two designs until we are satisfied with the design. There are a few benefits to do the PCB design in 2 steps rather than design the PCB directly. The schematic is useful to understand the circuit and debug the circuit, and the schematic will tell the layout designer what parts are on the PCB and how they are connected, so there will be less error to design the PCB in the 2-step process. Now we will talk about terminologies in the PCB design. The first 3 words in the PCB design is part, footprint, and package. The part is used in the schematic to represent components. The part contains information about the connection of the components, such as number of pins and name of pins. The footprint is used in the PCB layout. The footprint is often linked with the part in the schematic. The footprint contains information about the location of the copper path. The package refers to the physical shape of a component. When we are choosing a footprint, we must make sure the footprint matches the package, so we will be able to solder the component onto the PCB. Package is a defined set of dimensions of components. It will determine the footprint on PCB, position and size of the path to solder components. The same part may have different packages. The manufacturer may pack the same chip into different packages to fit different situations. Let's use 18MEGA328P as an example. It has 3 different packages. A dual inline or DIP package is suitable for breadboard, perf board, or through-hole soldering. A quart flat package or QFP package is suitable for general surface mount soldering. A quart flat no leads or QFN package is suitable for high-density surface mount soldering. For parts like resistors and capacitors, they also come in different sizes. Generally speaking, a larger resistor will have a high power rating, and a larger capacitor will have a larger capacitance or higher voltage rating. I would recommend 0805 size components because they are large enough to be soldered easily and small enough to save a lot of space. You may use 0603 or smaller components for more compact circuits, or you can choose larger components if you need a bigger capacitance. The word layer in PCB often means the layer of copper in a PCB. For example, the single layer PCB only has copper on one side of the board. The small perf board in the class kit is a small piece of single layer phenolic resin board. You will see the copper only exists on one side of the board, and there is no copper in the holes. The 2-layer board has copper on both sides of the board, and there are copper on the inside of the holes. The green board in the class kit is a 2-layer fiberglass epoxy board. This type of board is the most popular PCB in prototyping. 4 or more layer boards are made with multiple thin 2-layer boards laminated together. The 4 or more layer boards has the advantage on signal integrity, and they can make more compact circuits. For example, an iPhone is using a 10-layer board to make a high-density circuit. A network is a collection of 2 or more interconnected components. In the schematic, the object can be wired together or share the same net label. For example, on the left image, the pin 46 of the main chip and the pin 2 of J3 are both connected to the SWD-IO network. Although there is no wire connecting them, they have the same net label, so they belong to the same network. In PCB layout, objects in the same network should always be connected with traces, because you need a copper trace to form an electrical connection in the real world. Paths are exposed copper areas that you can solder legs of components to. Surface mount paths are copper on one side. Through-hole paths are copper on both sides with a hole to fit the leg. In this image, a diode is resting on 2 surface mount paths, and there are 2 through-hole paths on the sides. This type of design is compatible both to surface mount part and through-hole parts, and either part will work on this PCB. Traces are strips of copper that connect paths and vias together. They have the same functionality to wires on the breadboard. If you need a trace to carry a large current, it is better to use a wider trace to get a larger cross-sectional area. Vias are holes to connect different sides of the board together. They are generally small and not exposed. Here's a quick quiz. How many paths are there on this PCB, and how many vias? There are 16 paths on the PCB. 10 of them are surface mount ones, and 6 of them are through-hole ones. There is no vias on the PCB. A 2-layer PCB has 7 different layers of materials: top silk screen, top solder mask, top copper, substrate, bottom copper, bottom solder mask, bottom silk screen. Let's take a look at the PCB on the bottom on this slide. The substrate is not transparent, and we will not see any layer on the bottom side. The most top layer is the silk screen layer. On this PCB, it has a white color. The silk screen layer is often used to show information for humans to read. The next layer is solder mask layer. On this PCB, it has a green color. The solder mask is a thin protective layer of polymer protects the copper traces from oxidation or being soldered, and the solder mask may be clear to be see-through. The next layer is the copper. It forms traces, paths, and vias. Some of the copper is exposed, and some of the copper are protected by the solder mask. The substrate provides mechanical support for the whole board. Copper forms traces, paths, and vias. On regular green solder mask PCB, the copper traces will appear as light green traces under the solder mask. For hot air solder leveling finished boards, the exposed copper is in silver color because the copper is covered with thin layer of solder. For electroless nickel immersion gold finished boards, the exposed copper is in gold color because the copper is covered with thin layer of nickel and gold. Solder masks cover all areas that shouldn't be soldered, and it can be in different colors. The most common color is green, but depending on the manufacturer, the other colors may be available. The silk screen is often in white color, and it shows information for humans to read. Design rule check will check a few rules for manufacturability, such as trace width, trace distance, hole size, whether your connection matches schematic, etc. In real world, there are a lot of limitations on the manufacturing of the PCB. If one trace is designed too thin, the manufacturing process may break it. If two traces are designed to be too close, the manufacturing process may breach them, and if the hole is too small, the factory may not have a drill bit for it. Here, we will use OSH Park's rule as an example. Note the PCB design often uses a length unit called mil, which is 1/1000th of an inch. So there is 6 mil minimum trace width, 6 mil minimum spacing. These two rules are making sure that your traces won't break or bridge. At least 15 mil clearances from traces to the edge of the board. This will make sure the inaccuracy of the board counter routing won't damage your traces. 13 mil minimum drill size, which should be their minimum drill bit size. 7 mil minimum annular ring, which keeps the drill hole on the copper area. Here's a demo about how the PCB is made.
Once these steps have been completed, holes are drilled to connect the individual layers. There are various types of holes, such as vias to connect the individual layers, or component holes that are needed for the subsequent population of the PCB. The next step after the drilling is the through-hole plating process. In this process, holes are cleaned, activated, and given a thin copper coating to create a vertical electrical connection between the conductive layers. The outer layers are then processed. Firstly, a laminate is applied. This lamination process is similar to the inner layer process. In the photopositive method, the areas that are not needed for the PCB layout are exposed. The aim is to expose the areas that will subsequently be plated. In the following step, the unexposed laminate is removed. Then, at the exposed copper areas, the copper coating is plated up and the final copper thickness is attained. A layer of tin is applied to protect this copper layer for the next three processes. The first of these processes is photoresist stripping, in which the polymerized photoresist is removed. Then the areas not covered with tin are removed in an alkaline etching process. Finally, the protective tin coating is removed. At this point, the circuit board is already electronically functional. Now, the protective and finishing processes are carried out. The first step of these finishing processes is to apply a photosensitive layer of solder resist. This protects the PCB against corrosion and mechanical damage, and during soldering, it prevents solder from being applied to the areas covered with solder resist on the PCB. It also improves the electrical properties and dielectric strength. Like in the previous photo processes, the desired surfaces are protected against exposure. In the subsequent development process, the solderable area, solderable pads, and the component holes are uncovered. Then, a solderable surface finish is applied. This could be, for example, immersion silver, immersion tin, electroless nickel immersion gold, HAL, or lead-free HAL. Temporary solder resists or protective tapes can be applied depending on the requirements of the following solder processes. One of the last steps is the application of the desired annotation via screen printing. The final mechanical processing ensures that the multilayer gets its final shape. Here, this is done by milling. Before the multilayer shipped out, we carry out electrical, optical, and dimensional inspections of the PCB.
There are a lot of small details that may ruin your design. Here's a good book to see the common things you need to remember. The book is called PCB Design for Manufacture, published by C Studio. It's a free book and you may access it from C Studio's website. Here's a little quiz from the book. Here are 4 PCB designs. Why the 2 design on the left is better than 2 design on the right? The upper right one has 1 trace across the pad, and the wear stop will increase the risk of bridging. The lower right one has 1 trace on the side of the pad. The trace is closer to the other pad, and it also increases the risk of bridging. There are many circuit design software you can use to design a PCB. Here we will talk about the most common ones. Altium Designer is a quite powerful PCB design software. It has adequate difficulty in learning. Now the Altium Designer has multiple versions: the free Circuit Maker version, the low-cost Circuit Studio version, and the high-cost Altium Designer version. It only runs in Windows. Cadence is another high-end software for circuit design. Cadence is more powerful and more complicated to use, but it has an advantage in developing complicated circuits. For example, Apple uses Cadence to design products. Eagle is popular PCB design software in the maker community. Eagle's advantages are it is cross-platform and lightweight. There is a vibrant community, so there is a lot of contributed library. Both SparkFun and Adafruit use Eagle, so the most common parts are covered. Eagle has a free version for makers to design simple circuits, and there is a free education license as well. If you prefer open source software, KiCad will be a good option. KiCad supports all platforms such as Mac, Linux, Windows, and Android. It is an open source software and it is free.